Pues nada, estamos por aquí. Voy a dejar esto en pantalla de momento. Vamos a ver a qué el señor octogenario dando clase. A ver. ¿Cómo pongo la cámara? Es una mierda, ¿no? En general. Sí, a lo mejor. Oh, mientras me pongo las gafas. Oh, qué pelo me llevo. Vale. Mala suerte. A ver. Vamos a ver. Voy a comprobar que se está oyendo el directo y empiezo. Hoy básicamente voy a ver al señor Mayor dando clase de matemáticas de geometría computacional. Le daré a por 2 probablemente o por 1,5 y cuando vea algo que de verdad me interesa. Sí. A ver.
We're primarily interested in drawing triangles when we're rendering three-dimensional objects because we'll use triangles to...
Sí, vale. A ver, ahora tengo que quitarle la voz. Perdón. Así. Esto se queda aquí y ya está. Ya tengo chat y ya tengo esto. Pues para nada, para adelante. Vamos a ver.
form surfaces of solid objects, but we'll start with drawing points and lines first. And this is taken from section 1.3 of the online textbook of the current draft.
¿Hay un textbook aquí?
Look there as well. So let's start with drawing points.
¿Hay un textbook? No hay textbook, vale.
So let me draw a small picture with x-axis and y-axis, there are 3 points in the plane. So here will be the point 2, 1. Here will be the point 2, 2. And here's the point 0, 2. And we want to just draw these 3 points, presumably we'll be drawing the pixels at those points. So in C++, what we do is we'd start off by putting these points in an array. So we just use an array of floats. So float verts. To render anything we wanted. But that would obviously be very awkward to render a picture in terms of just setting every pixel separately. So we want to instead move up to lines next, and let's talk about that. For instance, a sample type of commands right here on a pen plotter. So for pen plotter, if you wanted to draw the triangle, and somehow the same triangle I had last time when our JavaScript canvas element to GL, and I'll discuss those in just a second on the next board. So there's 3 modes that illustrate these with examples. So let's suppose we have 6 vertices. There's V0, V1,
No.
V2, V3, V4, let me put V5 over here. So I've got 6 vertices, V0 through V5. And if I do a GL draw command, I'll do GL draw arrays. And if I do it in GL lines mode, I'm drawing 6 vertices. What that does is it draws pairs of lines, or draws lines between pairs of vertices. So it draws a line between the first and the second vertex, V0 and V1, the third and fourth vertex, V2 and V3, and then the fifth and the sixth vertex, which is V4 to V5. You can also do GL draw arrays with GL lines trip. Begin with the same 6 vertices, and what this would do is would add in the connecting vertices. It would connect also in addition to those 3 lines I already drew, it would draw the green lines connecting V1 to V2 and V3 to V4. I drew that one wrong. There we are. The corrected line is from V3 to V4, and this is just giving the strip of lines. It draws a total of 5 lines. If there's
Vale, bien, me da
6
igual.
vertices.
Esto es hacerlo.
Open GL mode.
Vale, esto es lo que me
GL
interesa.
triangles mode. And
Que no me acuerdo.
which or other GL draw command, we'll see there's more of them. GL triangles. And I'll do an example with 6 vertices. So there could be V0, V1, V2, V3, and join them fully filled in. And then the second set of 3, and we fill that in as a triangles in counterclockwise direction. V3, V0 here, triangles by the single called GL draws. And I'm going to put little, we're looking of those face. The back face is the other side. And And how do we tell the difference between the front face and the back face? Well, it's from the direction of the vertices. When we're looking at the front side, it's V0, V1, V2 come in counterclockwise order. V3, V4, V5 come in counterclockwise order. If we were looking at the back side of the triangles, you'd see V0, V1, V2 in clockwise order, going instead of going this way, going this way. And you can tell OpenGL to handle, or shader programs actually to be more specific, to handle front faces differently than back faces. You can also tell it to not draw the back faces and only draw the front faces. For instance, if you were drawing a solid figure, you might not want to render the inside of the figure, just the outside of the figure. And so in this sense, it's important for that reason to keep track of which faces are front and which faces are back. And for that, the order of the vertices is important. Okay, so the next example is GL triangle fan. V0. Draw the little circular arrows for the counterclockwise direction. These things indicate the front faces. So again, as I've drawn it here on the board, we're looking only at the front faces. If we went to the back side and looked, we see the back faces, but the direction of the vertices on each of these, they go in counterclockwise direction. Particularly the starting ones, V0, V1, V2, are in counterclockwise direction for the front face, and then the front face of one triangle connects to the front face of the next triangle as you go around. Arranged somewhat differently, ladder type shape. The first triangle has V0, V1, V2, and we're looking at the front face, they go in counterclockwise order. The next one has V1, V3, and V2. The next triangle has V2, V3, V4, and the final triangle has V3, V5, V4. And so, again, these are all front faces. So in other words, sort of three.
Correcto.
For the first, here's the North Pole, South Pole to V1, V5, 9, V2, V3, V4. Here. So let's try this. So now I'm going to made it 0 and this triangle strip rectangularly. So here's the at the top are the same as the vertices of these as the last strip going across the sphere. Let me call that now W0. And we're building, I'll fit it down here on the board. Would use vertices W0, W2, 5, 6 as a triangle fan. So by putting together these triangle fans and triangle strips, we could also render the sphere in this fashion. Okay, that's the end of this presentation. The next presentation.
Okay.
Hello, in this presentation we'll talk some more about how triangles in a 3D image get mapped onto a rendered image on the screen. So in this setting here we've got a three-dimensional scene,
Pero luego voy a
which is typically rendered as triangles.
Sure.
With all shapes are typically going to be rendered with triangles, and possibly with lines as points as well, but for solid objects, they usually use the triangles. And the triangles model the surface of the objects. So in particular, we talked about the sphere last time. We have a sphere. We broke the surface of the sphere up into triangles, and we then let the triangles approximate the smooth shape of the sphere. And it's also going to be rendered with a view or camera position and direction. In other words, someplace there's a viewer, which I'll draw with a sort of stylized eye shape. This is meant to be an eye or a camera. And the viewer is looking in this direction at triangles in the scene. And we want to take those triangles in the scene and map them onto the viewplane, onto the image as seen by the viewer, mainly what we render, say, on the computer screen or in the photograph or whatever. Okay. And so in that way, we change the 3D triangles into a 2D image. But now, obviously, not all triangles are visible to the viewer. First of all, there could be a triangle behind the viewer. Right? So here's a triangle behind the viewer that's not visible, sheerly because the viewer is looking in the other direction. Or then there's another, here's a triangle, I really need this triangle to be on the inside of the sphere, so the viewer is looking at this front face, and if there were a hole in the sphere, would look over and see the back face of the triangle on the other side. So remember, all triangles come with front faces and back faces. They're given by the counterclockwise.
Oh, un segundo. Mamá, dime. por culo. Viene la gente. Impresionante.
Rule normally, and we could just say here that we can call, and that's call means the same thing as discard triangles that are not visible to the viewer. And so some of them get automatically called, like the ones that are behind the viewer in the opposite direction that the viewer is looking, automatically get called by OpenGL. It's taken care of for you. You don't have to do that. But then other ones, like here's a triangle that's on the inside of the sphere, facing inward towards the viewer, but the viewer is outside the sphere, so we know ahead of time that the front side of the sphere is going to hide the back side of the sphere, and so we can also call back faces in this case. So when rendering closed, solid objects, surfaces, we can also call back faces. We can also call back faces. Of course, that assumes that we've correctly modeled the surface with the front faces facing outward from the surface and the back face inside the sphere. So pretty much I already described calling. Let me just give you the OpenGL commands that are used to enable for GL call face. GL dis underscores. Okay, good. You can also change the conventions on counterclockwise versus clockwise. As described as vertices V0, V1, V2 are in counterclockwise order. That's the front face. And you can, however, also change the conventions to make the opposite face the front one with calling GL front face GL CW. CW for clockwise, CCW for counterclockwise. The viewer is outside of a solid on it. There is, however, a second reason why this triangle on the inside is not visible, and that's because the triangles on the front of the sphere are hiding to the viewer the triangles on the back of the sphere. So this is called hidden surface removal. If a surface is hidden from the point of view of the viewer because of triangles in front of it, we also don't want to show it to the viewer. So I'm going to talk about next about how to detect hidden surfaces. Increase the viewer, being that if some triangle, method number one is what I would call geometric analysis, how they overlap. So here, loosely speaking, you would do the following. Consider all pairs of triangles in the scene. Figure out how they overlap each other. And then render only the visible parts. So the kind of things that could happen is I could have, let's get some colored markers here. So for instance, I could have a green triangle that's being partially blocked by a red triangle. So think there's a green triangle in the scene, and there's also a red triangle, and the red triangle is closer than the green triangle. Well, we would say you don't see the green triangle at all. Instead, you see the red triangle. So this would get, the green, say, gets filled in with green, the red gets filled in with red, and you would see something like this. So with the geometric analysis, you would figure this fact out, and since we're only rendering triangles, we'd probably break that part of the green triangle into two pieces. We'd render the green triangle as three smaller triangles, and the red triangle could just be rendered as itself. And of course, there's many different ways this could happen. I could have the green triangle blocked in this way. That's going to be a straight line there by the red triangle. So here, there's the green parts visible here, and the red parts visible in here. And we could even have a more complicated thing where the green triangle and the red triangle interpenetrate each other. Let me see if I can draw that here. So here's the green triangle, and it's not entirely behind the red triangle. The red triangle sticks into it. So the red triangle, I draw it sort of at an angle, and it sticks in, but try it again. It sticks in, but it's not entirely sticking in. It's like a thing like this. The red triangle is penetrating into the green, and advantage is ahead of time of triangles before you can do this analysis, because in principle you want to do all pairs. There's ways to make it faster, so you don't have to literally do all pairs, but then you also need to write a fairly sophisticated algorithm to make this all work reliably. Okay, so it's not all that easy to code. You also have to redo this every time, say, the view position moves. You must redo the work whenever things move, in particular whenever the viewer moves. So it has a lot of disadvantages. So method 2 will be the painter's algorithm. So method number 2 is the painter's algorithm. And the painter's algorithm has a very simple idea. You sort the triangles so that the furthest triangles from the viewpoint or the camera get rendered first, and then you successively sort closer and closer triangles to the viewer, and you let the closer triangles overwrite
Pero hace
So we
overdraw.
render all the triangles, but we only end up seeing the ones that are not hidden by the closer ones. So we sort triangles by the reverse distance from the viewer. So further away ones come first from the viewpoint. And we then render farther away triangles first, and closer ones last, and the closer ones overwrite the ones they hide, or the portions of the ones they hide. So a picture of this would be, we have two triangles, green triangles further away than the red. So the green triangle get drawn first. Even the portions of it that will be hidden get drawn first. Now when we say draw this, we're drawing it into an array of pixels. So when we draw a triangle, the triangle is specified by the vertices, and then each triangle covers some pixels on the screen, and we just, of course the pixels aren't quite triangular, but we just draw the pixels green that are covered by the green triangle. And then we come along and we draw a red triangle, and it's closer, so maybe the red triangle is here, and it's closer than the green triangle. So what we do is we just draw the red triangle too, and what that does is it overwrites the green triangle's pixels, and we just fill in the red triangle pixels.
Correcto.
And in this way, we just
Okay.
to a certain extent, this is how
Overdraw.
many painters actually operate, or some painters operate. This is called the painter's algorithm. So if a painter's drawing a scene, say you've got a Renaissance scene with a castle with a horse that's behind, and so this way the painter can draw each component separately. He can draw the background without having to worry what the castle looks like particularly, and he can draw the castle without having to worry about what the horse looks like particularly. And so this inspired the name of the painter's algorithm here. So there's obviously some advantages to this. You don't worry particularly how they interact. You just overwrite, so you don't have to think about it. The disadvantages are you do have to have all the triangles first and sort them, or have some other method of sorting them. Right? If somehow you know that some things are further away, you might just render them first and then render the closer thing second. And again, if the viewer moves, or it's a disadvantage. So it could happen that we have three triangles arranged so that each one covers the next. So I could have three triangles like this. Then the thin part of the triangle blocks the green triangle, and this part of the green triangle blocks the black triangle. So the triangles are interleaved. The black one is over the red and under the green is over the black and under the red is over the green and under the black. So here there's no way to sort them. You can't draw the red first, or the green first, or the black first. So in this kind of thing, the painter's algorithm will fail. Not a particularly common thing, but it's definitely a disadvantage. So there may be no way to consistently sort by distance. Okay. When we're drawing, we'll say a color value. That'll be the color that the new thing. When we're drawing a triangle, we render the triangles in any order. 2 pixels. And after we render a pixel, we compare previously written depth. What's closest, that pixel on that triangle to the viewer. And if that depth value indicates that it's closer to the viewer than the old value inside the pixel, we overwrite the pixel's color and depth values with a new color and depth values. Otherwise, we keep the old closer. So you can see this, again, lots of advantages to this. It's a very simple idea. It depends heavily on the pixelization, but the advantages are, right, it's simple. Geometric comparisons are that. We have a lot of vertices, a lot of triangles, and a lot of pixels, really a lot of pixels, all being processed more or less in parallel, pipelining results from one stage to the next. But it doesn't matter which triangle is being handled first. If they get a little bit out of order, the depth buffer method takes care of that. There are some disadvantages, of course. Nothing in life is mostly that you need extra memory for the depth values. So you need an extra 32 bits per pixel on your screen. 32 bits is a common thing. So, you know, there could be millions of pixels on your screen, but memory nowadays is pretty cheap. So memory is cheap, so I'll just say that's not such a bad advantage. This was a bigger disadvantage a few decades ago when memory was more expensive, but nowadays it's quite cheap. We also have inherent in this, but actually any transfer to pixels, is what's known as aliasing problems. Aliasing problems we'll talk about later on. It's any time we're converting from some analog, or perfectly smooth process to a digital process, or discrete process. So here, the analog or digital or smooth screen, so we don't have a perfect matchup. There's a few still images that do by hand. Digital movies now have fuzz. I can 6 or higher. The basic idea is that essentially still images. You maintain how the new becomes the, and then method overwrite. If you were formed, in your eye. So the way this is done on the computer is in OpenGL. There'll be the front buffer, which I'll draw sort of a rectangular thing. And this is the current image being displayed on the monitor or wherever. And so as we're animating a scene, we render a scene at one point. It's in the front buffer, and that's what the user's seeing. So while the user's looking at that, the computer is working on a back buffer, which is a completely independent section of memory. And this is the next image, which is being formed, being created. So for instance, with the depth buffer method, if you were to look at the back buffer, you would see triangles start appearing, and then other triangles overwrite them because the depth buffer method overwrites them, and then eventually the whole scene would be there. All that should happen in less than the 60th of a second, and then once the next image has been formed, we swap the two buffers. The back buffer becomes the front buffer becomes the next back buffer. We clear the back buffer out, the new back buffer, the old front buffer out, and we start rendering the next image after that. So we swap buffers, which doesn't mean really that we swap the data in the buffers, we just swap the buffers, their roles, to switch the... At any point, the user is just looking at a fixed still image. The other back buffer is changing as it's being created, but the user doesn't see that. And this is the method used to create animated motion. All right, that's the end of this video, so thank you very much. Hello. In this presentation, I will talk about flat versus smooth shading. So I've already pre-written a bunch of stuff on the board for you. First of all, this is in materials in section 1.4, especially 1.4.3 for flat shading in the PDF online. And I've already written on the board for you a copy of a vertex shader and a fragment shader, very simple, that render triangles with colors on the vertices. So the vertex shader has an input, which is the vertex position, and a second input, which is a vertex color. They're both vec3. The position is x, y, z values. The vec3 is for color is an RGB value, red, green, blue values. The vertex shader runs on each vertex. All it does is pass through the position. We assume that the position is already in the right range to work well with the fragment shader, and pass through the color without changing it. This is done by declaring a variable to be an out vec3 vert color, or the color, put variable in vec3 the color. Here it is output for each alt mode. Triangles with vertices v0, v1, v2, and v3, and we're thinking of doing. And what the smooth shading does is it takes the colors on the vertices as output by the vertex shader. And when the fragment shader, which the fragment shader runs on some pixel, it may run on a pixel here, it could run on a pixel here, it could run on this corner pixel, and so forth. When it receives the input color is an average of the colors on the triangle. So this pixel here on the left-hand row with RG shader will be, we're going to get one pixel on the right, so that has no colors. So now corner one vertex of the triangle and applies the color to the whole triangle. So the color of, in fact, the last vertex
Eso no lo sabía, ¿ves? Eso está bien saberlo.
is used throughout the triangle. So how this works in the flat range here to say, because it was in triangle mode, flat. And so what happens then is every pixel
No, esto ahora.
data from your C++ code for all three-way attributes. Corner values, or can be filled as a big array of data. Each vertex has its own data value. They stay the same. These values are still values associated with the vertices, but they stay the same for all the vertices given attribute. The second way is a so-called generic vertex attributes. These are not stored in the video, and in fact, they stay the same. These values are still values associated with the vertices, but they stay the same for all the vertices given a single GL draw command. So this is the same. These are the same values for all vertices.
Correcto.
But they can change between calls to G. These are also the same for all vertices in a single GeoDraw call. So some differences here. The values of type 1 and 2 the vertex shader. On the other hand, uniform values, these are the things of type 3. These can be accessed by both the vertex shader and the fragment shader. Matrix are often made available as uniform variables, e.g. the Mulligan matrix or the projection matrix. We will talk more about these as we get into it, are often uniform values. Sometimes the variables. Because sometimes the fragment shader actually wants to use these matrices for transformations, such as when we get long lighting and so on. So, just to list briefly the OpenGL commands that are used to access these things.
Espera, sí.
The vertex here. That's the trig is short for a bow. Out. What of her vertex attributes. Do not store the data in the DBO. If you're switching between storing the data in the DBO and then not storing the data in the DBO, we call GL disable vertex and triple array to undo GL. This is the 3F is for 3 matrices. Means in other words, we see third column, fourth column, total of 16 numbers. GL uniform matrix FP just takes a pointer to an array of 16 floats and loads those in as the current value of the uniform variable that goes to that matrix, or the location number of the vertex shader links to the values in the C++ program. Uniform variables have a dynamically allocated location number, at least in the most commonly used versions of OpenGL. And so we actually have to get it each time we run the program because it could be different every time we run the program. How these things are used that are line vertical or overlapping triangles. They change.
Qué barbaridad, vale.
Triangle works. So the vertex on the DBO.
Vale, me parece bien. ¿Ves? Esto sí que me interesa más.
Hello. This presentation will start the mathematical part of the course. We'll be talking about linear and affine transformations. For simplicity, we'll start working with R2, but mostly we're interested in R3 because we're talking about 3D computer graphics. I want to mention first how they fit into the graphics pipeline, how transformations are used, and then we'll get into the mathematical constructions. And this is taken from the first part of chapter 2 in the book, which is available online as a PDF file. So the graphics pipeline, in its simplest form, has a series of transformations that are applied to points or objects to place them in 3 space and then place them on the screen for viewing in the image. So we start off with some points, which I'll call X. X denotes a point in R2 or R3, and this is in so-called local coordinates. And the first step here typically is to transform this by a model matrix M, and we form mx, this is m times x, in world coordinates. And this is done with a model matrix M that transforms the point x. And this usually, we have a world coordinates means we've got x, y, z space where our 3D objects are living, and we place the object in world coordinates. Now, we want to view this object from some particular point of view, so we transform it again. We apply another matrix V mx up to mx, which of course is the same as Vmx. And this gives the points in so-called view coordinates. So here we're thinking of the viewer is specified by matrix V, found in space. The location of the points on this image that we're looking at, it takes into account things like perspective, that things look smaller if they're further away, and so forth. Step to do the full transformation into screen coordinates. And typically these matrices M, V, and P are operating on points in 3 space, but they're actually going to be 4x4 matrices, as we'll see in future lectures when we get to that topic. But they're actually going to be 4x4 matrices, as we'll see. So I've got a Ferris wheel, a chair. So the artist would build a chair in local X might position might depend on time and so forth. So M with VMX gives the position of the Ferris wheel relative to the viewer and describes would map the point to some pixel. Okay, so let me switch and talk about linear transformations. So I'm going to talk about linear transformations in R2 or 2 space. Typically we'll want to really work in R3, but the mathematical theory is almost identical for R2 and R3, and it's a lot easier just to visualize and draw things on the board. So I'll start working R2, and later on we'll talk about how to transform this all to R3. So points in R2, they're given by XY coordinates. So I'm going to denote a point as a X with a vector sign over it like that. In the textbook, it's denoted as a boldface X. I don't use the vector sign notation in the book, I use a boldface X. And what this means in R2 is that it's a pair of points. X1, X2. X1 is the so-called X coordinate, X2 is the Y coordinate. We might also write it as XY, that's a different X, not boldface. X and Y here are now scalars. This is the X component of the point and the Y component of the point. And these are really viewed as column vectors. So strictly speaking, this means the column vector X1, X2. And this means the column vector XY. So points are column vectors. 2. So that's math. I'll use either capital A, capital B, and so on as names for transformations, or function names like the equals alpha of a times x plus y for all point transformation. This is just the same thing as the usual linear transformations like you learned about in linear algebra. There's nothing. If a is linear, then a of the zero vector is equal to the zero vector, where here's some new notation. Zero vector is the origin, the vector 0, 0. The proof is very simple here. Nations y, two conditions for linear. The y-axis and y here is the rotation of 90 degrees, or pi halves radians, around or pi halves, depending on whatever we're supposed to go. That's linear. The transformation that doesn't move anything at all is clearly linear. And then also the zero transformation, which maps everything to zero, a of. We're going to try some examples of things that are not linear. A transformation 2 to R2 is a of x. So this t sub u is just the identity. X plus 0, point at all. T sub u is not linear. And one way to see this is that it doesn't map the origin to the origin, since, for instance, u, so it's not x, b. So clearly, translation is a special case of an affine transformation. So translations are affine transformations, and also every linear transformation is an affine transformation, because you can just take u equal to 0. So as one final definition, let's talk about the composition of two mappings. This is the usual definition of composition of functions. If A and B are transformations, then their composition goes to B, x, compute A of that. So transformation, of course, U plus U forward. Okay, so this lecture will stop here. The next one will take up techniques for visualizing the effects of transformations in R2. Thank you.
Thank you. Qué barbaridad de persona. Vamos a ver.
How to visualize transformations in R2 is most and you for through think of their transformation. We point this map to the F shape, but very can try map it for
no sé si estas son.
Once you know the origin space of a vector, let's try it. So here I'll S alpha beta of x1.
Okay.
Negative, you're getting trace of x.
Esto es lo que me interesa.
1 plus 1. So out. Maps the F. T a little bit harder. What happens is that it's just this point becomes 1, 1.
But
this point becomes 2, 2, and the rest of the points fill in as expected. 1, 2, and 3, 1. For linear, and to a lesser extent for F, that linear that fits into the picture. Denote x or y with vector signs over them are column vectors, members of this two-dimensional vector space. So we might have x is the column vector x1, x2, and we also use notation with angle brackets. Angle bracket x1, x2, although it's written as a row, with the angle brackets there, what I'm signaling is that I really mean it to be a column vector. And the whole point of this is merely to save space when typesetting, so that a row of numbers takes up less space than the column of numbers when it's typeset in the book. So the angle brackets mean vectors, J, B the I. The components, U has two components, U, V1 and V2. And we're going to use these to give a matrix representation. Matrix with is equal column x2, the first n. A applied to a sum is the sum of A applied to the components of the sum. To you, there's claim.
Vale, sí.
Sitting
Escalares, multiplicaciones.
And the line matrix. Here I put the vector signs back on. That means that U is a column vector of length 2 because we're R2. This example, theta, CCW, means that we've got the plane R2, which is our I. Think about angle theta up here. sine of theta, that's the x component, and sine of theta, that's the y component at this point. And likewise, the point J is going to come angle theta this way. It's going to have component minus cosine sec, and then we're not going to replicate h as usual. This one into f is and the of J. It's 1 and 1. So I'm representing affine transformations with matrices.
Vale, vamos a ver este vídeo.
The first thing I want to have a look at is how we represent color on a computer. If we take this light green color, or any color for that matter, then we can represent it as how much red, green and blue goes into that color. Write it as a three-dimensional vector. I already textures. A texture is nothing more than a bunch of colors arranged in a grid, and I'll make that grid a bit more obvious here. We can assign an index in the horizontal direction as well as the vertical direction. Grids can be This is just an aid for it that the texture is supposed to represent texture in the thing. Given this 3D model, in this case a cube, and this texture, in this case an image of the 6 sides of a dice, UV mapping is a technique that allows us to stick that image onto the 3D model. In this case, that will give us a dice. The way this works is by defining a coordinate system around our texture. The top left corner of the texture will have coordinates 0 and the bottom right corner will have coordinates 1. We call the horizontal axis the U axis and the vertical axis the V axis, which is where the name UV mapping comes from. To now map the texture onto our cube, all we have to do is define a UV coordinate for every vertex that makes up the cube. For example, these front 4 vertices can get mapped onto the UV coordinate system like so. We now store these UV coordinates as vertex attributes of the corresponding vertex. If you're paying close attention, you might notice that there are vertices like this one that can map to multiple different points on the UV coordinate system. The way we solve that is by adding 2 vertices into the vertex buffer. They will share the same position but will have a different UV coordinate. Since vertex attributes get interpolated across a triangle surface, we can determine the color of any point on our 3D model. Let's say we have this point, then the computer can tell us what its you can and outputs a color thing called a sampler and you can just think of it as a function which takes in a U and a V coordinate and outputs drawn a UV coordinates contained which for every point a very steep range clamp function. Result word being track the functional mirror part of X and the unit.
Vale, sí, cago en Dios. Ok.
Cavities at 2 by 2 are always for.
Thank you.
Creo que voy a cambiar la forma en la que hago esto porque no tiene sentido estar aprendiendo mates que ya sé. Lo que voy a hacer es, a partir de ahora, los lunes también voy a hacer gráfica. Y en el momento en que entre en algo de gráfica que no entienda las mates, entonces iré y miraré esas mates. Que si no, no tiene sentido porque estoy literalmente en bucle mirando cosas que ya sé. Sí que es verdad que hay detalles concretos que mola saber. En plan, oh, no sabía esto, no sabía esto, cosas sueltas, pero no tiene sentido gastar una hora entera para aprender 5 minutos de cosas nuevas, ¿no? Entonces, vale. De todas formas, hoy lo que queda ya voy a intentar tirar por aquí hasta que encuentre algo que no... ¿Ves? Lo de rotaciones y tal... Venga, otra vez. Dime. Vale. ¿Qué te iba a decir, pero ya que me he quemado? La carne picada está acá aguando, ¿no? me está dando por culo, o sea que voy a pirar. No tiene sentido esto. Vale, pues eso, a partir de ahora los lunes también